Hey guys, this is Gilsdorf. Sorry, I smacked my lips so hard right then. So I wanted to work out one of these problems because I realized that when I was kind of going through it, it makes sense to me when I see it, but it may not make sense unless you see it actually done. Okay, so this is just going to be a practice problem video. I'm just going to go through one of the practice problems. So right now I'm on the back side or page 2 of section 3. Which is calculating initial and equilibrium concentrations for reactants and products. Okay, so again, we're just really trying to track here what is happening to these things. So we have in this reaction, it says for a system, we start with a certain amount of CO2 and H2. We're asked for final concentrations of everything. So once it reaches equilibrium. Now we know that the rates of the forward reaction and the rate of the reverse reaction are going to be the same at equilibrium, but we don't necessarily know which side is greater. So we don't necessarily know whether the concentration of one or the concentration of the other is greater. So let's go ahead and color code. So the first one, CO2, this is CO2. We have H2, we have carbon monoxide, or CO, and then we have H2O. Okay, so we are told that the initial concentrations of CO2 and H2, which are both reactants, so I'm going to see if I can jot that in there real tiny. So that's a reactant, that is a product, and a product. Okay, so what that means for us is that the reactants, we should see a decrease in their concentrations because they're going to be used as we go forward in the forward reaction. Products, we will see, just kidding, we will see an increase in both of our products. Okay, so the products are both going to go up. The reactants should both go down. All right, so in order to do one of these, which is called an ice table, again because of initial change and equilibrium, in order to do one of these, we have to actually see what is the change that's happening. Okay, so in this first one, it went from 0.1 down to 0.08. Okay, so I don't feel like doing math because, you know, whatever. So I'm going to say 0.1, 0.008. So 0.1 minus 0.008 means that this one changed by a value of 0.092. Okay, and it went down by that amount. So let's look at the equation to figure out, okay, is this value x, or is this value 2x, or 3x, or 4x, or whatever the case may be? So in the equation, we notice that it actually is balanced. It is a 1-to-1 to 1-to-1 ratio. So that means that this value of 0.092 is x. That is the overall change. That is the basic change that we're going to see. And we know that because CO2 did not have a coefficient. If CO2 had a 2 in front of it, then this is 2x. Okay? Now, some people like thinking about it with the variables. Some people don't. It doesn't matter to me which way you like to think about it. If you like the variables, that's fine. If you don't like the variables, that's fine too. You can just deal with the numbers. So the reactant went down by that much. So the other reactant is going to go down by a similar ratio. In this case, the ratio is 1-to-1, so it's going to go down by the same amount. It's going to go down by 0.092. Oh, that's not 0.092. So both of the reactants are going to go down by the same amount. The products are going to go up by their same mole ratio as well. In this case, CO2 to CO is a 1-to-1, which means this product is going to go up by the same value, 0.092. CO to H2O is also a 1-to-1, so this one is also going to go up by 0.092. I can't, whatever, it's in there. No, that's ugly. Y'all know I can't deal with it being ugly. 0.092. I mean, it's all ugly because I can't write on screen, but whatever. So, in this second one, 0.1 went down by 0.092, so we would expect the same amount, 0.008 molar. So both of these would be used up at the same rate. Both of them are going to go down to the same final concentration. Both of the products go up by 0.092, so we can expect 0.092 molar to be the final concentration of carbon monoxide, and 0.092 molar to be the final concentration of H2O. That is not a 9. had been a 2, so if one of these values right here had been a 2 or a 3 or anything, then these values would have just been multiplied by that value, okay? So let's say, for example, that I had, instead of a 1 here, I had a 2. Then that means that for that particular reactant, I would have just taken this and multiplied it by 2. Okay? Now, like I said, that was not the case for this one, so I can't say that. But if it were, I would have just said, oh, okay, times 2. Okay? Or let's say, for instance, this one, let's say that one was a 2. Then that means that that was considered 2x, and all of the rest of these would be divided by 2. Okay? So it's really just looking at a situation and saying, okay, based on the initial and the final concentrations, what was the overall change, and how can I interpret that change on different sides of the reaction based on different mole ratios? Okay? So in this case, last step is looking for, well, which side of the reaction is the equilibrium going to be on? On the left-hand side here, we see that the total concentration between both reactants and then the total concentration between both products, the products are greater. And so what that means is that the equilibrium position is on the product side. 0.092 and 0.092 added together is greater than 0.008 and 0.008 added together. So we have more on the product side, and therefore the equilibrium position is on the product side. All right? So again, if you didn't attempt this one, that's fine. You can have it now. Attempt the next one. If you want to send it to me have me check it before you do the practice, that is fine by me. But if you are feeling good about it, then you keep on trucking, do the practice on calculating KEQ and ICE tables, and then submit that once you have checked the key, and then check Google Classroom for the rest of your assignments. All right.